Alkyl nitrites are the alkyl esters of nitrous acid, which more specifically are the set of compounds with a distinctive nitrite group attached to a carbon backbone. The initial members of the alkyl nitrite series are volatile, with methyl and ethyl nitrite being gaseous at the 20 degrees Celsius definition of STP. Most of them have a distinctly sweet and soft fruity odor. These compounds have notable biological effects due to being a source of nitric oxide, which signals for the relaxation of smooth muscles, such as that of the gastrointestinal tract or the cardiovascular system. As such, alkyl nitrites are potent vasodilators, expanding blood vessels, lowering blood pressure, and increasing heart rate. Due to the lowering of blood pressure, this often induces headache and facial flushing. The chemical and biological properties of alkyl nitrites primarily derive from the nitrite group, as the alkyl group itself is just some unreactive carbon shenanigans. The onset of effects is rapid, typically about 30 seconds, with all nitric oxide and hence the effects being depleted within a few minutes. Acute toxicity arises when extended exposure to alkyl nitrites and hence nitric oxide oxidize hemoglobin in the blood to methemoglobin. Methanoglobin cannot carry oxygen, leading to a condition known as methanoglobinemia. This can cause nausea, vomiting, hypertension, shortness of breath, and fainting. Severe cases cause oxygen deprivation, which require emergency treatment with oxygen and intravenous methylene blue, which helps reduce methanoglobin back to hemoglobin. Now that we understand the safety risks, it is to be noted that even when not working under a fume hood, the amount of alkyl nitrite vapors is negligible. So, if one is careful, inhaling enough vapors to the point of oxygen deprivation is highly unlikely. However, getting a headache from the vapors is possible. Hence, it is advised to work in a ventilated area or a fume hood. Now, let's see how we can synthesize an alkyl nitrite. As a general note, the total time required for this procedure is around 1 to 2 hours. To do this, you'll need 3 key components: a strong acid, a nitrate salt, and an alcohol without interfering functional groups. First, let's understand the role of each component. Nitrous acid is unstable in solution, so we generate it in situ by reacting a nitrite salt, usually sodium nitrite, with a strong acid. The acid itself must be stronger than nitrous acid to effectively protonate the nitrite base, forming nitrous acid. For practical purposes, the most suitable and obtainable acids are hydrochloric acid and sulfuric acid, where it is to be noted that the sulfuric acid is able to protonate twice. The chosen alcohol must lack functional groups that could interfere with the reaction between the alcohol and nitrous acid. Suitable alcohols should also not produce gaseous nitrates at STP or alkyl nitrites with excessively high boiling points. Examples of such alcohols include propanols such as isopropanol, butanols such as butanol, amyl alcohols such as isoamyl alcohol or isopentanol, hexanols such as hexanol, cycloalkanols such as cyclohexanol, halogen substituted alcohols such as 2-chlorobutanol, and ether alcohols such as 2-ethoxyethanol. Of course, this is a non-comprehensive list, so if you are able to find another alcohol that is suitable, you may as well use it. Avoid using alcohols that are too large, such as those with more than 6 or 7 carbons, or those that are heavily substituted, like 1,1,2,2,3,3,3 heptachloropropanyl. These larger or highly substituted alcohols can and will refuse to fractionally distill, even under vacuum, making purification difficult. By carefully selecting the right acid and alcohol, you can efficiently produce your desired alkyl nitrite. In this case, the acid, salt, and alcohol I will use will be sulfuric acid, sodium nitrite, and butanol respectively. Now, let's get on with the procedure. First, we make a solution of sodium nitrite by weighing out 13.5 grams of sodium nitrite, or 2 molar equivalents, and topping it off with water until we reach approximately 60 milliliters of volume. The dissolution of sodium nitrite is endothermic, so expect the process to take a minute or two. We then prepare an ice bath. The ice bath is critical, as elevated temperatures not only will cause our butyl nitrite to evaporate and our yields be shit, but also result in the decomposition of nitrous acid into various nitrogen oxides. Note that, even with an ice bath and slow addition of sulfuric acid, nitrogen oxides will still evolve, albeit to a limited extent. In the ice bath, we place a round bottom flask, and we first pour in the 20 milliliters of butanol, or 2 molar equivalents, then the sodium nitrate solution, and a stir bar. In an addition funnel, we measure out 5.1 milliliters of sulfuric acid, or a little less than 1 molar equivalent, that we already pre-chilled in the freezer at -6 degrees Celsius, and slowly drip it in dropwise, with intense stirring, or more specifically, a stir setting of 7 out of 10. During this addition, especially on some larger alcohols like cyclohexanol, you may be able to see the transient blue color of nitrous acid as the sulfuric acid drops hit the solution. The sulfuric acid is the limiting reagent because excess acid will catalyze the decomposition of butyl nitrite. Let's go over the mechanism. First, sulfuric acid protonates 2 nitrite ions and generates 2 nitrous acid molecules. Then, each nitrous acid molecule protonates an alcohol, forming a good leaving group. In conjunction, since the nitrite ion is a good nucleophile, it attacks the protonated alcohol in a SN2 reaction to form the alkyl nitrite and give off water. Overall, the general reaction can be seen here. After addition is finished, transfer the solution to a separatory funnel and remove the bottom water layer while keeping the top nitrite layer. Note that, although some nitrites are supposedly clear, this crude nitrite layer will always be yellow. Now, transfer the nitrite layer to a round bottom flask and set up for a fractional distillation. Note that for heavier alcohols, you may need to perform a fractional vacuum distillation or even a fractional short path vacuum distillation. While the majority of the boiling points of alkyl nitrates are available online, and those that aren't can be approximated by the Joback method, in practice, these boiling points are grossly overestimated. When using boiling points available online, take the fraction with ranges of 4 to 5 degrees Celsius below the stated boiling point. For instance, isopropyl nitrite in practice should be collected around the range of 36 to 40 degrees Celsius. Butyl nitrite in practice should be collected around the range of 73 to 78 degrees Celsius. Furthermore, boiling points calculated from the Joback method are even more of an overestimate, with the calculated cyclohexyl nitrite boiling point being around 130 to 150 degrees Celsius, while in practice, it should be actually collected around 108 to 112 degrees Celsius. After we collect the reasonably pure butyl nitrite fraction, we are to pre-stock its storing container with an acid-neutralizing agent like sodium carbonate, a drying agent like sodium sulfate, and a radical inhibitor like butylated hydroxytoluene to prevent acid-catalyzed hydrolysis, and radical hydrolysis, respectively. After transferring the butyl nitrite over to this pre-stocked container, we are finished. Hopefully, this video was informational or helpful in some way to your chemistry journey. And, as what for butyl nitrites or alkyl nitrites in general, I guess, may be most practically used for, well, go get pegged and find out, I guess.